Yeah, okay, so I think we can start now. Uh, yeah, so this talk, the title of the talk is, as you can see it is Foundation of Hardness. So, so hardness of a problem can be of multiple types, right? It can be hardness of time. So basically, where we prove that some problems are hard in the sense that you cannot have a polynomial time algorithm for them, right? Am I too loud? Okay, so uh, 1 second. Can we adjust the volume? Hello, am I audible? Okay, thank you. Yeah, yeah. Okay, fine. Yeah, so I was talking about this hardness of a problem can be of multiple types, right? So it can be about hardness of time. So it's basically about the area where you prove that some problems cannot have polynomial time algorithms or say algorithm that runs in order n square time, right? And it can also be about hardness of a space. So basically proving that some problem cannot be solved in order log n size space. And it can also be about hardness of approximation, right? So basically you prove that for some problems you cannot have a good approximation algorithm in polynomial time, right? But in this lecture we will only focus on time, okay? And even there we will not prove that some problems are hard. Okay, we will prove that some problems are hard assuming that some other problems are hard. Okay, so if there are some problems which cannot be solved in polynomial time, then there is some other set of problems that can also not be solved in polynomial time. Okay. So yeah, so this is the outline of the talk. So I will spend first slide on justifying why we focus only on decision problems in this theory of hardness. Okay, so I mean this theory of hardness is only about decision problems, not about optimization problems. Even when I think in real life optimization problems occur more often than decision problems, right? So I will justify why we work only with decision problems. Then we will see what is NP completeness, and finally we will prove some problems like not three sat, but independent sat, vertex cover, dominating set, and k-center. All these problems are NP complete. Okay, so it's a very basic lecture. I hope that I know that most of you might already know about this, but since the rest of the workshop is about only about algorithms and all, we thought it would be nice to have at least 2-3 lectures. Okay. Yeah. Uh, yeah. So I hope, I mean, even those who already know about NP completeness, they will learn uh, I mean, one in this sequence, right? I mean, probably they will see some new reductions in this lecture. Okay. It's not working. Yeah. Okay. Yeah. So first, let's see what is optimization problem. So optimization problems, we usually have in problem, you usually have a set of solutions, and for every solution, you associate a value with it, right? And then in optimization solution, you want to find a solution with the best possible value, right? So for instance, you have this minimum vertex cover problem, right? So given a graph G, you want to find the smallest size vertex cover of G. Okay, so this is one optimization problem. There are many others like shortest path problem, right? Or longest common subsequence problem, right? Now, what is decision problems? So decision problems are those problems which can be posed as yes or no question. Okay. So basically, given the input, you have to answer whether that input satisfies some property or not, right? So for instance, here you can see one decision problem called vertex cover. And in this problem, you get one graph G and you get one integer K. And you have to tell whether there exists a vertex cover of size K in G. Okay. So let me ask you a question here. Can we solve vertex cover problem if we have an algorithm for minimum vertex cover problem? Yes. So it's you have to just solve this right? Then depending on the size of the okay. Yeah, and then depending on the size of the input of the smallest vertex cover that you've got, right? You can answer yes or no, right? Okay. And can we say this also? Uh, that is, if minimum vertex cover is polynomial time solvable, then so is vertex cover, right? And then just take the contrapositive of this, that if vertex cover is not polynomial time solvable, then minimum vertex cover is also not polynomial time solvable, right? So this is why we can only focus on decision problems, right? So if we take this vertex cover problem and prove some hardness result about it, right? It will also imply an hardness result about minimum vertex cover problem. Okay, but I mean, this is why it doesn't hurt to focus on decision problems. But why do we need decision problems? And the answer is because it simplifies a few things. Okay, so things like reductions that we will see in next slides. Okay, so let me start with this complexity class called P, which I'm sure you all know. Okay, so many problems of our interest are easy, right? I mean, they can be solved in polynomial time. So here, just one more thing, I'm using it for my convenience, that I'm not writing decision problems purely as decision problems. I'm writing them in the form of a set or language, right? So basically, for every decision problem, you have a corresponding language or set, right, which is made up of only yes instances, right? So for instance, if you have this path decision problem, where you get G, U, V, and K, and the problem asks to find a path of length at most K from U to V, right? The corresponding language or this set path will just be the collection of all the yes instances of this problem. Okay. So throughout the talk, whether I'm saying decision problem or language or some set, it basically means the same thing. Okay. So we have some problems, right, which are solvable in polynomial time, easy problems like path, longest common subsequence, even basic operations like multiplication. We know we can do it in polynomial time. And so we have this very important and well-known complexity class called P, which is the set of decision problems solvable in polynomial time. Okay. Okay. Uh, Unfortunately, not all of our problems, which are important for us, not all those problems are solvable in polynomial time, right? So vertex cover, we know by now that we do not have a polynomial time algorithm for general graphs, right? And similarly, this problem called Hamiltonian cycle problem, this is also not solvable in I mean, we do not know any polynomial time algorithm for that. And same we can say for graph isomorphism problem, right? But here's the thing. So even though we do not know polynomial time algorithm for these problems, there still is a commonality between among these problems. And the common thing is that even though they are not easily solvable, they are not solvable in polynomial time. Uh, if someone gives you a solution to these problems, right, you can verify whether that solution is correct or not in polynomial time, right? So for instance, for vertex cover, if someone gives you some subset of the graph G, right, you can easily check in polynomial time whether it is indeed a subset of graph G or not, right? So, so these problems form the class NP. So informally, it captures the a set of decision problems whose solution can be verified in polynomial time. And this is the formal definition of NP. Okay, so we say that a decision problem L is an NP if there exists a polynomial time algorithm M, right? So this algorithm M takes two input. It takes X and it takes U. Right? And U is the length of U is some polynomial of X. Okay, and what this algorithm do is that X belongs to L if and only if there exists some U such that M of X comma U will be equal to 1. That is, M of X comma U will output yes. Okay. So suppose you want to put vertex cover in NP using this formal definition. What will be your M? So X will be the graph. What will be U? I mean, what will M do with U? Right. I mean, you will treat U as the subset of G, right? And then you just check whether it is indeed a vertex cover or not, right? And similarly for Hamiltonian cycle, right? You can check whether a particular sequence of vertices is forming a Hamiltonian cycle or not, right? Okay, so this way we have this class called NP. Okay, so its full form is actually non-deterministic polynomial time, basically, right? But so there are basically two definitions of it. So this is one definition. Other definition uses the idea or notion of non-determinism. So we have non-deterministic Turing machines or algorithms, right? But I'm not getting into that in the interest of time. And I mean, there is a section of community which also feels that this notion of non-determinism is not necessary. I think even those who propose it believe that okay, this definition suffices. Okay, so we'll not get into the non-determinism. We'll just work with this definition. Okay, so yeah, so we have this class called NP, and we do not know whether P is equal to NP. Okay, the famous question, P versus NP. Okay, but what we do know is that P is contained in NP, right? I mean, this picture actually doesn't correctly depict it. It is giving the impression that the P is properly contained in NP, but we do not know this yet. But anyway, my motive through this picture was only to show that P is contained in NP, right? So this is one thing we know. What else do we know? We know that there is a subset of NP. Okay, there is a set of problem in NP, which are the hardest problems in NP. Okay. So formally we say, and we call it NP complete problems. Okay, and its formal definition is the following. So a decision problem L is in NP if it is NP complete, if it is in NP, and all the problems in NP are polynomial time reducible to it. Okay. So what do I mean by when I say that NP complete forms the hardest set of problems in NP? This will become clear when I go over what is reduction and all, right? So let's first see what is reduction. So reduction is basically a technique where you take two languages, say L1 and L2, okay, and you map instances of L1 to L2, okay, and you map it in such a way so that you map yes instances of L1 to yes instances of L2, and you map no instances of L1 to no instances of L2, right? And I mean, more formally, we say that a decision problem L1 is polynomial time reducible to L2 if there exists a polynomial time computable function f such that for every x belongs to L1 if and only if fx also belongs to L2. Okay. So here is one observation. Yeah. So if L1 is reducible to L2, then we can say the following. We can say that if L2 is polynomial time solvable, then so is L1. Yeah, you have a question? Yeah. Yeah, yeah, it is possible. So we are not, I'm not saying that that mapping has to be onto or injective. Okay, it's just mapping that yes instance should be mapped to yes instance and no instance should be mapped to no instance. That's it. Okay. Yeah, so yeah, so I was saying that we can say the following, that if L2 is polynomial time solvable, then so is L1. Is this clear to everyone? Right? Because what you can do for L1 is that uh, what you can do for L1 is that you take its input x, right? You reduce it to L2 and then you solve L2, right? So that way L1 is also in polynomial time solvable. Okay. So this reduction can be used for two things. I mean, reductions in general can be used for two things. They can be used to show tractability or showing that some problems are easy. So suppose you want to show that some problem L1 is in P. So all you have to do is reduce that problem L1 to L2, where L2 is already known to be in P. Okay, and similarly, it can also be used to prove hardness. So if you want to prove that L2 is not in P, right? All you have to do is reduce some language or decision problem L1 to L2, where L1 is already known to be not in P. Okay. So this was about reductions. Let's get back to NP complete problems. Yeah. So that's up to you. I mean, if you want to prove that some problem is NP complete or you want to do this reduction, right? I mean, this is what you have to come up with. Right. Yeah. Yeah. Yeah, of course. Yeah, we know. Of course, we know. I mean, so actually proving this, uh, So what we know is that, like right now, so this class NP, right? We suspect that it is not equal to P, right? So we'll see in a minute that NP complete problems, right? We believe that they are not in P, but this is what just we believe. Yeah. No. So halting problem is undecidable. So of course, everything which is undecidable, right, it is not in P, right? Because you cannot solve it with any amount of time. But there is a theorem in complexity theory called time hierarchy theorem. So what that basically says is that there is some problem which is solvable in n square time, right, which is not solvable in order n time. Okay. So actually, it is just a factor of log n. Okay. But for convenience, I'm just saying that not just n square n. There are problems which are which are solvable in n cube time, but they are not solvable in n square. Okay, and so on. But the issue is that that theorem doesn't actually give you some natural problem. It just proves. Okay, so uh, I'm sure, yeah, there must be some natural problem which are not in P, right? But just through existence, yes, yeah, there exist problems which are not in P. Okay, right. So yeah, so I was talking about NP completeness again. Yeah, so this was the definition of NP complete. And now we can say the following. So let X be an NP complete problem. Okay. Then we can say that P is equal to NP if and only if X is in P. Right. So this direction is fairly obvious, right? If X is an NP complete problem, X is also in NP, right? So if P is equal to NP, then X, of course, it belongs to P, right? Now, if X belongs to NP, how can you prove that P is equal to NP? So what you will do is that you take any problem in an NP, right? You reduce it to X. You can do it because X is an NP complete problem, and then you solve X, right? So that way, every problem in NP has a algorithm that runs in polynomial time, right? So this is what I meant when I said that NP complete problems are the hardest problems in NP. Okay? Basically, it just cannot happen that you have an NP complete problem which you can solve in polynomial time, but there is some other problem in NP which cannot be solved in polynomial time. Okay? So in that sense, NP complete problems are the hardest problems. Okay, so yeah, so all definitions and everything are fine, but yeah, yeah, yeah. Yeah, so yeah, you can say that, but I'm saying like I was only talking about NP complete. So NP hard is basically just those problems which can be reduced to. NP hard is basically those problems to which all the problems in NP can be reduced in polynomial time, right? So we do not. Yeah, you are right that NP hard problems, in some sense, they are harder than NP complete problems. Okay, and one example of NP hard is halting problem, right? Yeah. So I was saying, yeah. So definition and everything is fine, but how can we prove that some problem is NP complete, right? Because you cannot just go over all the problems in NP and give a reduction to that problem, right? So in one of the most exciting results of computer science, Stephen Cook and Leonid Levin, they showed that SAT and 3-SAT are NP complete. They also discovered the notion of NP completeness. And with that, they also showed that there are some problems which are NP complete. So SAT and 3-SAT are two such problems. And for this discovery, so Cook got Turing Award in 82 and Levin got Knuth Prize in 2012. Okay. So let me first define what is SAT and 3-SAT because we'll need their definition in the reductions that we are going to see now. Okay, so both these problems, SAT and 3-SAT, are about CNF formulas. Right. So CNF formula are what? They are basically Boolean formulas which are in the form of and of, ors of variables or their negations, right? So for instance, this is one CNF formula, right? It is just and of some clauses, and in every clause you are just taking or of some variables or their negations. Fine. So okay. So what is SAT? SAT is simply the set of all the satisfiable CNF formulas. Okay. And what is 3-SAT? 3-SAT is basically a set of all the satisfiable 3 CNF formula. So 3 CNF formula or a KCNF formula is a CNF formula, which is in which in every clause you have at most k many vertices, or sorry, variables or their negations. Okay. So this is the definition of SAT and 3-SAT. Fine. Okay. So yeah, so there is one thing about reduction uh, that is super useful for us, and it is transitivity in reduction. Okay. So what do I mean by transitivity here is that if L1 is reducible to L2, right, and there is some other language L3 such that L2 is also reducible to L3, then L1 is also reducible to L3 in polynomial time. Right? Why? Because suppose you have these functions, right? These polynomial time computable functions f and g, right? So f is yeah. No, this so this, if you saw the definition earlier, so this just denotes that L1 is reducible to L2. That's it. Okay. Hmm. Yeah, but you have to like modify the Turing machine so that you convert the instance of L1 to L2, right? Right. No, no, no. So that's what I'm saying. So L1, this sign just means that L1 in polynomial time is reducible to L2. That's it. Okay. So I think, okay, yeah, I'll not go back to the slide, but yeah, I wrote in the definition of reduction there. Okay. So all I'm saying is that if L1 is reducible to L2, okay, and L2 is reducible to L3, then L1 is also reducible to L3. Okay. How? So suppose f is the function, right? F is the polynomial time computable function that was mapping the instances of L1 to L2, and g is the function that is mapping instances of L2 to L3. Okay. Now for reducing L1 to L3, you can come up with a function which will be just this. Okay. So just composition of G and F, right? Is everyone okay with this? Okay. Yeah. No, we cannot. So, so see this example, right? I mean, you can basically take any language that is solvable in polynomial time, right? It is reducible to halting problem. Okay. So halting problem, I hope you know. But you cannot reduce. Of course, you cannot reduce halting problem to a problem in polynomial time, right? Because if you can reduce, then you are basically solving halting problem, right? So this reduction, I mean, it's not symmetric in nature. Okay. So it is transitive in nature, but not symmetric. Yeah. Yeah. Yeah, then it's yeah, of course, because L2 is NP, so it should be reducible to L1, right? And L1 is NP, right? Yeah, that's beautiful. Um, I don't know what's the definition of antisymmetry. Huh? Yeah, yeah, yeah. It, yeah. So I don't know about names, but yeah, I mean, it's not that if L1 is reducible to L2, then L2 will always be reducible to L1. Okay. Sometimes it will be. Yeah, yeah, yeah. So like I said, in case of halting problem, right? Yeah. Okay, so we have this transitivity in reduction that will be useful for us. Okay, so because of Cook-Levin's theorem, what we know is that all the problems in NP are reducible to SAT, right, in polynomial time. Fine. Now, suppose there is some other problem that we want to show that it is also NP complete. What we can do? We can either come up with some like similar great insight as Cook and Levins, right, and show that all the problems in NP are reducible to L, right? Or we can do simply this. We can reduce SAT to L, right? And this is how we grow this network, right? So we have, I mean, today I think the number of NP complete problem probably runs into thousands. Okay. So this is just one small subtree of that large network. And we have lots of natural problems that we know are NP complete. Okay. So of course it is not possible to prove all of them NP complete in one lecture, okay, or half an hour. So we'll focus only this small section, like I said. Okay, so we'll assume that 3 set is, yeah, like we know that 3 set is NP complete, and using that we will prove that independent set is NP complete. I will define what is independent set. Then we'll show that vertex cover is NP complete, and then dominating set and K center. Okay. So any questions before we start these reductions? No? Okay. Okay, so we'll start with 3 set to independent set. Okay. So 3 set we already know, it's a set of all the satisfiable 3 CNF formulas. What is independent set? Independent set is basically given G and K. You have to tell whether G has an independent set of size K. Okay. So in case if no one knows, if anyone does not know whether, I mean, what is independent set, then it is just a subset of vertices of G such that no two vertices of that subset have an edge between it. Okay. So for instance, in this graph, you can find an independent set of size 3. Yeah. Self loop. No, you can assume that, yeah. I mean, it's not important. You can like define it your way. But here we are assuming, let's assume that we don't have this notion. I mean, we don't have self loops there. Okay. Yeah. In the graph, we are assuming there are no self loops. Okay. So is the definition clear of independent set? Okay. So, okay, so let's see the reduction now. Our goal is to convert phi. Okay, so phi is some CNF, 3 CNF formula, and we want to convert it into G, a graph G, and some value K, such that G has an independent set of size K if and only if phi is satisfiable. So suppose you have one clause, okay, one clause of length 3. Okay, I mean, you have U1, U2, and U3 in it. So how many different possible assignments to the variables you can have? No. 2 part 3, right? We can have 8 possible different assignments, right? And out of them, how many will satisfy this clause? 7, right? Okay. So what we'll do is that we will take one clause. Okay, so we are converting phi into G, right? So what we'll do is that we'll take, suppose you take the first clause, okay, and suppose it is this, and what we'll do is that with respect to this clause, we will add 7 vertices in the graph G, okay, and all these 7 vertices correspond to the values or correspond to the partial assignment that is satisfying this clause. Okay, so here you can see the only assignment that will not satisfy it is all zeros, right? So that's why we do not have a vertex corresponding to 0, 0, 0. Okay, so this we will do for one clause, then we will do for the second clause. Suppose this is your second clause, right? So here the only value that will not satisfy this clause will be 0, 1, 0, right? So here again we will have some 7 many vertices, right? Fine, and this you will do for all the clauses. Okay. So in total, how many vertices our graph will have? So 7 into number of clauses, right? Okay. So this is about the vertex set, right? But we also have to put some edges there, right? So the first thing what we'll do is that in every cluster, right? In every cluster of these 7 vertices, right? You put an edge between every pair of vertices. Okay. So I mean, this picture is not quite depicting what I'm saying, but uh, there is an edge between every. So there will be an edge between V1 and V2, V1 and V3, and so on, right? Yeah, you can say it's like a clique of 7 vertices. Okay. Yeah, yeah. Okay. But these will be edges only inside a cluster, right? Okay. Now, what about the vertices which are in different clusters? So what we will do is that we will take one vertex from one cluster, okay, take another vertex from another cluster, and we will put an edge between them when they are corresponding to inconsistent partial assignment. Okay. So what do I mean by that? So suppose you take V8 here, okay. So V8 has what? It has values what? It has, for U1 it has 0, for U3 it has 0, for U4 it has 0, right? And suppose we pick V4 here, right? It has 1 0 0, right? So U1 is 1, U2 is 0, U3 is 0, right? So they are inconsistent. Why? Because in V8 U1 is 0, right? But in V4 U1 is 1. Okay, so this way they are inconsistent. So every time we find two vertices like this which are inconsistent, we put an edge between them. Okay, and this we do with all other vertices also. Like we'll put an edge between V8 to V5 and V6, V8, V6, V8, V8 and V7. Okay, I think there should also be an edge between V1 and V8, but it's okay. Yeah, I'm just saying that between two vertices you put an edge when they belong to or they correspond to inconsistent partial assignments. Fine. So let's write this more explicitly. So in converting phi to G and K, we create a cluster of 7 vertices for every clause. If phi correspond of a cluster of 7 vertices corresponding to satisfying partial assignments, right? Moreover, we add an edge between every pair of vertex in the same cluster, and we add an edge between two vertices of different cluster if they correspond to inconsistent partial assignments, right? So is our reduction complete, or do we still have to like do something? No, I'm saying, is the reduction is complete or not? No, this is the function. Yeah, we still, so we have defined K, right? From phi we have defined G, but we haven't defined K yet, right? So this will be our K. K is the number of clauses in phi. Okay. So let's prove now, like you said, we still have to prove that this works. So our claim is that phi is satisfiable if and only if G has an independent set of size K, okay, where and K is equal to M, right? Number of clauses in phi. Okay, so let's do it in 2 steps. First, we'll go the forward direction, and then we'll go backward direction. Okay. So suppose phi is satisfiable, right? Then there must be some satisfying assignment U, right? So what I will say now is that we can form an independent set S of G in the following way. All you have to do is that you have to pick a vertex from every cluster, okay, in G, in such a way that its value should match to the value of U. Okay. Now, what do I mean by that? So let's 1 second. Let's get back to the diagram. Yeah. So suppose you have this satisfying assignment U to phi, right? And it is assigning value to U1, U2, and U3 1 0 0, right? So in the first cluster, you will pick V4. Okay. And let's say to U1, U3, U4, it is assigning that satisfying assignment. It is assigning all ones, right? So in that case, in the second cluster, you will pick V14, right? Now, if we are picking our vertices this way, how many vertices we will pick? K many, right? K or M, right? Okay. Now answer me this. Can there be an edge between two vertices that we have picked? I mean, any two vertices that we have picked? They cannot be, right? Because we are picking them according to U, right? Which is like a valid satisfying assignment, right? So we cannot pick two vertices which correspond to inconsistent. And we put an edge only when they were inconsistent, right? So this proves the forward direction, that if there is a satisfying assignment, right, you can have an independent set of size K or M in G. Okay. Now let's get back to the backward direction. Yeah. Okay. So yeah. So now suppose G has an independent set S of size M. Using that, how we can create a satisfying assignment for phi? So first thing that we have to notice here is that if G has an independent set S of size M or K, right, S must have exactly one vertex from every cluster, right? Because there are M many clusters, right? You cannot pick two vertices from one cluster, because if you're picking two vertices from one cluster, there will be an edge between them. It will not be an independent set, right? And you cannot leave any cluster because there are only M many or K many clusters, right? So you will pick only one vertex from every cluster, right? And now using all these vertices, right, all you have to do, so all the vertices that you have picked, right, they were satisfying every clause, right? And since it is an independent set, right, no two vertices are giving you in any inconsistency in the assignment, right? So what you can do is simply is that you will take the assignment corresponding to, let's say, one vertex. Say that vertex is about u1, u2, u3. Okay, and you start creating u from that. Okay, so you will in u you will give the same value to u1 as there was in that vertex that you picked, right? So u1, u2, u3 will be same in u, right? Then you pick then the second vertex of the cluster using the values of that second vertex. You can again add some more. You can assign some more values to the satisfying assignment there, right? So this way, if you have an independent set S of size n, ultimately you'll be able to find a satisfying assignment for phi. Is that clear? Okay. Yeah. Okay, so this completes our first reduction. Let's see the second one. So it is from independent set to vertex cover. So vertex cover, I believe you all already know. In case you do not, it is just the subset S of vertices, such that for every edge UV, either U or V is in S. Okay. So for instance, here you can see that it has a vertex cover of size 3. Right. I doubt there is any smaller vertex cover. Okay. So yeah, let's look at the reduction. So again, our goal is to convert G comma K to uh, G comma K to G prime and K prime, right, in polynomial time, such that G has an independent set of size K if and only if G prime has a vertex cover of size K prime. Okay. So can anyone guess what will be the reduction? Complement. You take the complement of G. Right. So yeah, so our G, we'll simply copy G to G prime, right? Our G prime will be G. We are not doing any modifications in the graph, right? And K prime will be n minus K. Okay. So let's see the proof. The proof is very simple, actually. So this is the claim. So let's see the forward direction. So suppose D has an independent set S of size K, okay? And then I claim that V minus S, right? That is the set S, and you take out all the elements of S from it, right? That set will be a vertex cover. So suppose it is not a vertex cover, we'll prove it by contradiction. So suppose V minus S is not a vertex cover. Then there must exist an edge UV, right? Such that neither U belongs to V minus S nor V belongs to V minus S, right? But if both U and V do not belong to V minus S, U and V should belong to S. And if U and V both belong to S, and we know that there is an edge between U and V, then S cannot be an independent set, right? So this is not possible. Hence, like, this addition is over, right? So V minus S, we know it is a vertex cover. So let's look at the backward direction. So suppose the proof is again very similar, and it's very simple. So suppose G has a vertex cover S of size n minus K, then V minus S will be an independent set. So again, assume that V minus S is not an independent set, right? Then there must be some edge UV such that U belongs to V minus S and V belong to V minus S. Right? Okay, so if this is the case, then U comma V cannot belong to S. But if U comma V cannot belong to S, and we know that there is an edge between U and V, right? Then S cannot be vertex cover, right? Because no one is covering that edge. Okay, so this is also not possible. And this completes the reduction. Okay, so the third one. So has anyone any question? Okay. Okay, so this is from vertex cover to dominating set. So how many of you already know what is dominating set? Okay. So, okay, yeah, so I will define it then. So G prime, okay. So vertex cover is clear. So dominating set is simply, in the dominating set problem, you get your graph G prime and K prime, right? And you have to tell whether G prime has a dominating set of size K prime. Now, what is a dominating set? We say a subset S of vertices of graph G prime is a dominating set if for every vertex of the graph, okay, either that vertex or its neighbor is in S. Okay? So this is the definition of dominating set and the dominating set problem. Okay, so for instance, here in this graph, you can see that it has a dominating set of size 2. Sorry, which one? Okay, sorry, I should have named it. Yeah, this one. This one. Yeah, right. Sorry, I missed it. Yeah, you are right. But okay, so let me ask a more interesting question. Is every dominating set a vertex cover? All right. So in this, can you form a dominating set, right? So like I said, that one vertex, right? Or you can say that, okay, these two, if you take these two vertices, it is a dominating set, but it is not a vertex cover, right? Yeah, in optimization problem, yeah, you want to find a vertex cover of minimum size, right? Or in dominating set also you want to find, right? But in decision problem, right, like I said, you just take that parameter and put that into decision problem, right? I mean, for a optimization problem, you can have a corresponding decision problem. And here we are concerned with just the decision problems. Okay. So yeah, so it is not the case that every dominating set is a vertex cover. What about the other way around? Is every vertex cover a dominating set? Is it? Okay, so suppose I put a isolated vertex here. Yeah. Yeah, so it is true to an extent. So in a graph in which we do not have any isolated vertices, a vertex cover is a dominating set. Okay. But in general, yeah, so there is a small case, right? So we'll see in the reduction, we have to basically take care of this isolated case. Okay. All right. So again, probably I'll bore you this time by saying this line again. So we have to convert g comma k into g prime k prime in polytime, such that g has a vertex cover of size k, if and only if g prime has a dominating set of size k prime. Okay. So let's see the reduction. So we have our g and k here. Okay, and let's see how we can construct g prime and k prime. So first step is to simply copy this graph. Okay. So we'll have like the exact same graph there. Okay. And then we will add some new vertices and edges. How we will do it? So suppose we take this edge UV. Okay. We take this edge UV, and for every such edge UV, we will add one more vertex W. And with that vertex W, we will add two edges, one to U and one to V. Okay. And this we will do with all other edges. So this will be our final G prime. Okay. So we are not touching isolated vertices, but with the rest of edges, we are doing this small surgery. Okay. So this is our G prime. What will be our K prime? Can anyone guess? Right, right, right. So I hope you guys do not know this already. Okay, you're guessing, right? Yeah. Okay. Yeah, good. So yeah, so like you said, so G prime is this, and K prime is K plus the number of isolated vertices in G. Okay. So let's prove this, that this reduction is correct. Okay. So okay. So our claim is that G has a vertex cover of size K if and only K prime has a dominating set of size K prime. Okay. So forward direction. So assume that G has a vertex cover S of size K. Okay. Then I claim that S plus isolated vertices of G forms a dominating set in G prime. So let's see why this is true. So we have this graph G for which we have this dominating set of size 2. Sorry, a vertex cover. Is this a vertex cover? Yeah, it is. Yeah. So it is a vertex cover for this graph, right? And from this, okay. So S, like I said, we will take S vertex cover, plus we will also take isolated vertices in the dominating set, right? And let's see why this set will actually be a dominating set in G prime. Okay. So let's go over all the vertices one by one and see whether see whether those vertices or their neighbor will be in this S plus isolated vertices. Okay. So let's start with the isolated vertices. So this is very simple, right? Because isolated vertices by definition, they are part of the dominating set, right? Okay. Now let's take some other vertex. So some existing vertices, right? Not the new vertices that we created. Okay. So suppose we have taken U, right? Now U is not an isolated vertex. So there must be a neighbor of it. Let's say it is V. Okay. Now what we know is that this is an edge, right? And at least one out of these two elements must be in S, right? Because S is the vertex cover, right? So either U or the neighbor of U will be in our dominating set, right? So existing vertices are fine. Isolated vertex we saw it was very simple, and other vertices we can like show them that they are not they will not create problem like this way. What about new vertices that we added? So W's, right? So how did we add W? Right? So what we did was that we had an edge UV, right? And for every edge UV, we added one vertex W, right? Now we know that one out of the vertex U and V must be in S, right? Yeah. So W is we know that at least one of the neighbor of W will be in this dominating set, right? So this direction is fine. Okay. Let's look at the yeah yeah. Which one? Yeah. No, that will not be problematic. Right? I mean, I'm not using the fact, right? Nowhere I use the fact that this vertex, these isolated vertices are part of. Why not? Yeah, right. Okay. So it will be extra, right? It will be only extra, right? Mm, yeah, yeah, yeah. Right, right. Okay. Yeah, yeah. Okay. So it is K prime. It is K prime. So K prime will be just yeah, 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 yeah. So you will only be double counting it. It will not create any problem. Yeah, yeah. Maybe we can do that. Yeah, 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 yeah. It will be a different reduction, but I'm saying this will also work. Okay. No, I mean I just defined my K prime to be K plus number of isolated. Right. I mean maybe we are doing something extra, but I'm saying it will not create any problem. Okay. Yeah, 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 yeah. Yeah, four. Yeah. No, I defined K prime to be K plus number of items. Yeah, yeah. But I mean, it will not hurt the reduction, right? I'm saying. Yeah. Okay. Yeah. 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 Okay. Yeah. Sorry. So here it is not three. I'm saying so. I just said that. I mean, this is just one example. Okay. I mean, here K is not the, I mean, uh, so K can be anything. K is actually the part of the input. I'm not saying like find the vertex cover of a smallest size. Okay, all I'm saying is that suppose G has a vertex cover of size K, okay, and I'm just explaining why this reduction works. All right. Yeah, yeah, yeah. Okay. Yeah, yeah. Uh, so those cases you can, yeah, yeah. Okay. Yeah, yeah, yeah. I understand that. Yeah, yeah, maybe. Yeah. Okay. 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 So this direction is okay, right? Okay. So let's look at the other direction then. Okay. So suppose G prime has a dominating set S prime of size K. Okay. So what we'll do here? So suppose, yeah, so S prime is the dominating set of size K prime. And now what we'll do is that we'll modify S prime to make it a vertex cover for G. Okay. Now the first thing that we will do is that we will remove all the isolated vertices from S prime. Okay. So this will not affect anything, right? If S prime was a vertex cover of G before this operation, then it will still be a vertex cover of G after this operation, right? Okay. So, but what this will do is that it will decrease the number of isolated vertices, right? It will bring down K prime to K, right? Because we have just removed all the isolated vertices. Fine. Now all we have to do is we have to do a few more operations, okay? And in each of these operations, the size of S prime will remain same, okay? So what we will do here is now is that suppose S prime is not a vertex cover, okay? So then there must exist some edge UV such that neither U nor V belongs to S prime, okay? And if that is the case, then what I claim is that this new vertex W, this should be an S prime, right? Because if because U and V were the only neighbors of W, right, in G prime, right? So if U is not in S prime, V is not in S prime, then W should be in S prime, right? So what we will do here is that we will remove W from S prime, okay, and we add U to S prime. That's it. And then we will again pick an edge which is not covered by S prime. We'll again perform this operation. And every time we perform this operation, we are keeping the size of this set S prime same. So finally, we will have a vertex cover of size K. Okay. Sorry. Okay. Yeah. This operation, this second operation. Yeah, 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 yeah. There we have used it. So all I'm saying is that if U and V are not, right? If U and V are in S prime, then we are fine, right? Because what do we want S prime to be? We want this S prime to be our vertex cover, right? So if U and V are in S prime, we are fine, no problem. But if they are not, then what we can do? Yeah, right? Mhm. Yeah, yeah, yeah. So I'm not modifying the graph, right? I'm modifying this. Yeah, yeah, right, right, right. Yeah, yeah. Why will S prime? Which condition? So number 3, or I mean number 2, right? So all I'm saying is that there is some edge UV, right? And both U and V are not in S prime, right? That's it, right? In that case, we'll perform this operation W. Okay. Now we look for some other edge, say U1 or V1, right? And both U1 and V1 are not in S1, in S prime, right? Then those U1 and V1 must have W1, right? Because their W1 we haven't removed it yet, right? That must still be there. We are only modifying this. Yeah, I mean, right. Other W's are still there, right? So no, so S prime. Yeah, I mean, our goal is to make S prime dominating set, right? Sorry, make it vertex cover. Make it vertex cover, right? So dominating set. Okay, so you are saying that maybe after this operation, it will not remain dominating set. Will. Okay, okay. Yeah, it will. Yeah, okay, I agree. Yeah, okay. Mm, maybe. I mean, actually, I doubt it will happen. Maybe it is possible, but all I'm saying is that, yeah, I mean, yeah, yeah. For all. Yeah, but yeah, you can. I think you can. Yeah, I mean, it's not necessary that you do all these operations in one sequence, right? Because for every UV, you will have its separate W, right? By construction, right? So it's not necessary you do it by this way, right? So maybe, I mean, your point. I think it needs some more argument that there will be no W by the end of this. Yeah, 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 it is possible. Yeah, right. So we are not actually implementing anything, right? I mean, this is just proof of correctness, right? What you have to implement is just the point 1 and 2. That's it, right? So you are not going to like actually prove this in your C program or write C++ program. Right? So what you have to implement are just the step 1 and 2. That's it, right? This is just about the proof of correctness. That's it. That something like this exists and you can do these operations. Okay, so I don't have much time now, but I will quickly cover the last reduction. Okay, so dominating set we already know. Before we get into the details of case center problem, so just consider this scenario that the government wants to build some K-many fire stations in a city. Okay, so what's the one thing they should definitely take care of? Huh? Everyone should be happy, or every fire station should be in working condition, right? Okay. I mean, so here's, yeah, as much area as possible, right? Okay. So right, right. So one way to say is that like every locality must have a nearby fire station, right? I mean, it should not be the case that uh, all the localities have a nearby fire station at the distance of 1 or 2 kilometers, right? But there are some 2, 3 localities for which the nearest fire station is at the distance of say 10 or 15 kilometers, right? I mean, that would be really bad. Okay, so case center problem is basically just this thing, right? So in the optimization problem, you get this. Okay, so let me define this way. So we get this tuple VDKR. I will define what is metric space. So the problem asks to determine whether VD is a metric space such that there exists a subset F of V, okay, of size K and radius R. So what is a metric space? So metric space is simply an ordered pair of 2 elements. So the first element V is actually a set, and d we can call it distance. So it is just a function from v cross v to r, okay, such that the following properties are satisfied. So d of x comma x equal to 0, uh, d of x comma y when x is not equal to y, it is greater than 0, and d of x comma y equal to d of y comma x. Okay, it should be the distance should be symmetrical, and is happening. Okay, yeah. So d of x comma z is smaller than equal to d of x comma y for some y plus d of y comma z. Okay, so basically triangle inequality. Okay. So this, I mean, these properties are generally there, right? I mean, if you look at the distance between different localities, right? All these properties are satisfied. So this is, I mean, metric space is just an abstract structure for all these like real life scenarios. Okay, so this is metric space. What is radius? So radius of a K center, so we'll call our F a K center. It is simply the maximum distance of an element from the nearest center. Okay. So basically what you have to do is that you pick one element in V, you calculate the distance to its nearest center. Okay. Then you pick another element, you again calculate the distance to its nearest center, and then you take the maximum of all of them, right? So this is the radius. Fine. So let's see the reduction now. Okay, so this is our goal, and we are mapping g comma k prime to vdkr. So what will be our v? Our v will be simply the set of all the vertices of the graph. Okay. What will be our d? So first thing, like because it is a metric space, so we have to ensure that d of u comma u should be equal to 0, right? So we have to put that. Apart from that, we will put d of u comma v equal to 1 when u and v are neighbors in G. Yeah. Yeah, sure, sure. One second. Yeah. Okay. So basically maximum of all the minimum distances, right? Fine. Yeah. So like I said, V will be VG, the vertex set of the graph. And yeah, so here d of u comma u equal to 0. And d of u comma v is equal to 1 when u and v are neighbors in G. Okay. And when u and v are not neighbors in G, then we put d of u comma v equal to 2. Okay. What will be our k? K will be equal to k prime. So any guesses about the radius? Those who already do not know. I know you learned it just 1 month ago, right? Right, right, yeah, right. So R is equal to 1. Okay, so let's see why it is correct. Okay, so claim again it is, so G has a dominating set of size K if and only if VD is a metric space with a K center of radius 1. This is what we have to prove. So again, forward direction. So suppose S is the dominating set, okay, of G of size K. Then I claim that F, which is like S in V, okay, because Vg and V are same, right? So F, which is equal to S in V, will be a K center of radius 1. Okay, so let's see how. So how can we prove that the radius of a K center is 1? We have to prove that every element in V has distance at most 1 to the nearest neighbor, right? So let's first pick those elements of V which belong to F. Okay. So suppose U belongs to F, and what will be the minimum distance of U from a center? It will be 0, right? Because U itself is the center, right? Okay. Now what about those vertices which do those elements which do not belong to F? How can we prove that they are distance to the nearest neighbor, to the nearest? Yeah. Yeah. Right. 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 neighbor of, right? So basically there will be some v, some neighbor of uv in G, right? Which will be in S. Basically it will be in F, right? So because F and S are same, right? Yeah, sorry. Right, yeah, right. Okay. And so basically we know that there is a V in F, right? Such that V will be in dominating set, or right? And we also know that they are neighbors. And by construction, right, from 2B, we know that when they are neighbors, the distance is what? Just 1, right? So that's why the distance to the nearest neighbor for even those elements which are not in F will be 1. Yeah, just 3 minutes. Uh, Okay. So, right. And what will be the radius? Radius will be the maximum of all these minimum values, right? So it will be 1. Okay. So this proves what this direction, forward direction. Let's look at the backward direction. So this time we are taking F to be a K center of radius 1, okay, for metric space VD. And we are claiming that S, which is equal to F in G, is a dominating set of size K in G. Okay. So how we can prove that S is indeed a dominating set in G? Well, you have to prove that, right? I mean, by definition, that every element, you take any element in G, either that element should be in S, or if it is not, then its neighbor should be in S, right? So we are taking only those elements which are not in S, and we'll prove that its neighbor will be in S, right? Okay. So, so we have taken this U, which is not in S, okay, and we know that there must exist a vertex, there must exist an element in F, such that its distance with U will be equal to 1. Because why? Because its radius, we know that the radius is 1. Okay. Okay. 0 is not possible because they are from different set. Yeah, yeah. 0 is not possible, right? Okay. So, but if radius is 1, then that implies that we must be a neighbor of U in G. Because this distance can be 1 only when, I mean, from 2B we can see that, right? It can be 1 only when they are neighbors. So that way, there will be a V, right? Which will be in S. Okay. And this completes the proof. Okay. So we have seen 4 reductions now. Thank you. Okay. Sorry? Two value. Two value is used here, right? This d comma u comma v equal to. So you're saying why didn't we use 3 or 4, something like that? So that will be covered in the lecture that will happen day after tomorrow. So you know that, right? Why we used to. Yeah. So we'll use it to prove some hardness of approximation. Yeah. 3 set 2? Okay, sure. Yeah. Yeah, it will work. It will work. But that 2 is important for something else that we'll see. Yeah. SAT to 3 SAT. That is simple. So basically, so in SAT, you can have a clause of like size more than 3, right? So, so just do this. Take this clause, okay, and create 2 partitions of it, right? And in every partition, and take this extra variable u, right? Suppose u, and in one partition, in one part you add u, in other part you add u prime. Sorry, u complement, and that's it. Right? So basically, this way you'll be breaking those large size clauses into smaller clauses. Okay, and you can, I mean, ultimately you will see that you cannot, this way you cannot reduce a clause of length 3 to clause of length 2. Yeah, yeah. So once again, so so suppose you have this clause of length more than length 3, right? U4, right? So what we'll do is that from this we will do or U and U3 or U4 or U. Okay. And what I say is that this is satisfiable if and only if both of them are satisfiable. Okay. But this will not work. I mean, so once you have this clause of length 3, we cannot like break it down further into smaller sizes, because if you do it, you will prove that 2 set is also NP complete, which is not. Right. Okay. So I think, yeah. Do we have 5 minutes or we are running out of time? Right? Okay. Yeah. So yeah. What was the question? Every clause? Right. No. So the construction is possible in polynomial. So you have just one clause, right? And with respect to that, you are only adding 7 vertices, right? And then you do the same for the other clause, right? So it's just like it is doable in polynomial time. Yeah. Right. 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 So how many it will be? M choose 2, right? Right. I mean, there are M many clusters, right? You have to pick any 2 clusters for putting H between them, right? Yeah. So it's still polynomial time, right? Yeah. Okay. So because of shortage of time, I will not be able to take more questions. We can talk after this individually if you want. Okay. Okay. Thank you.
Hello. No. Can you hear me? Okay.
Yes, I can hear you.